All right, so for number 11, we got a 20 kilogram object. Okay, so we draw our box, 20 kilograms in the middle, okay, is pulled horizontally along a level floor with a force of 27 newtons. Okay, if the object is accelerating, so they're giving us the acceleration, 0.80 meters per second squared, what is the magnitude of the force of friction? Okay, so friction always opposes, so I have to draw it back this way. The object is obviously accelerating forwards. Friction can't cause something to accelerate in the direction it's acting. Okay, friction doesn't work that way. All right, so I know that friction must be smaller than this force, so I have diagrammed it as such. What can I calculate right now?
The acceleration, or force mass.
Net force, because I have mass and I have acceleration. All right, so F net equals mass times acceleration. So that's going to be 20 times 0.8, which should be 16. All right, I think that's 16. Is that right? 16 newtons. Okay, so our net force is 16 newtons, and that would be, I'm just going to put positive, and I'll put positive on that so I indicate forward. Okay, so I've done the mass times acceleration part. I'm missing one of the two forces that adds up to this number, so the next step is vector sum of all forces. Okay, our applied force, the 27 newtons, plus the force of friction adds up to our net force. All right, so if I want to calculate that force of friction, I subtract applied force over to the other side, and that'll give me the force of friction. So that'll be 16 newtons minus 27 newtons, okay, is going to give me negative 11 newtons. And negative is really the only vector I can put on there. They didn't give me forward, backward. I can only say that it's opposite the other force. Okay, everybody all right with that? All right, that's a fairly simple one in terms of going backwards, right? Having the acceleration given and finding a missing force. Okay, now number 13, okay, is an elevator question. Works just like any other one, but they're wanting us to calculate the tension, so the lifting force, in 3 different situations. All right, so for situation A, okay, I've got the 1,200 kilogram elevator. Right? I know that there's a lifting force. All right, I'm just going to call it tension in the cable, and I know that there's gravity pulling down on the elevator. Everybody with me so far? Okay, can I calculate the weight, the force of gravity of the elevator? Okay, so that's just going to be m times g, and that should be 11,778 newtons, if my time's doing this question memory serves. Is that right?
72.
72? Okay, see, this memory doesn't serve me. 72. I was close. 72. All right, so we got that as our weight, our force of gravity. All right, now in part A, it is accelerating downwards at 1.05 meters per second squared. All right, so I'm going to say that my acceleration is negative 1.05 meters per second squared. Can I calculate the net force on the elevator right now? I can, just like the last question. Okay, so I'm going to go F net equals mass times acceleration, and I'm just going to go 1.05 times 1,200. Okay, so we got 1,260 newtons, but I should have made that negative. It's negative 1,260 newtons because it's down. Okay, now I need to find the missing force. So sum of all forces, F net equals gravity, okay, plus the force tension, and then I just isolate the tension force. Okay, that's going to be F net minus the force of gravity, so that'll be 1,260, negative 1,260, minus negative 11,772. They're both down. Right? When I do that, I get 1.05 times 10 to the 4. It comes out positive newtons because tension has to be acting up. Okay, everybody all right with that? Okay, is part B any different than part A? It's really, really close. All that changes is now it's accelerating upward. So in part B, all I do is take the negative off of this, okay, and the negative off of this, and there. Take the negative off of that. Now, that is obviously going to change things because now I'm not starting out with a negative number. I got a positive number plus 11,772, right, because it's minus a negative. So it makes sense, okay, in the first situation that the force in the cable is less than the force of gravity. That makes the elevator accelerate downwards. But in part B, if we're going to lift that elevator, the cable has to pull harder than gravity upwards. Okay, so now we're going to get 1.31 times 10 to the 4 newtons up. Because if the elevator is going to accelerate upwards, the tension in the cable has to be greater than the force downwards. Okay, C is the one that gives people trouble. Why? What's different about C?
Moving downward at a constant velocity.
Right, what are the key words there?
Constant.
Right, constant velocity. If there's no acceleration, there's no
Force.
F net. Right, there's no net force if there's no acceleration. If there's no net force, that's still true. It's just those two numbers add up to
0.
right, which means they're equal. One's up and one's down, but they're equal in magnitude. Okay, that's something that people miss. They just, like if I put this question on a test, they'll completely ignore that part. They'll treat that number like it's an acceleration and they'll do something like what we did in A and B. Okay, and they'll come out to the wrong answer. When this question here, okay, part C, because of all the work we've already done, requires no more work. Have you already calculated the weight of the elevator? All you have to do then is realize that the cable has to pull up with the same amount of force and plug in, put that number in as your answer. Okay, that's why it comes out to 1.18. This number here to 3 significant digits is 1.18 times 10 to the 4. Okay, everyone kind of follow there? Elevator questions, well, you know, when we set them up are pretty simple. For whatever reason, the context can really trick people. Okay. All right, keep going, and we'll do a few more here in a couple more minutes. Okay, let me know if you need a hand. All right, so obviously there's not much to number 15, like there's literally no math required for it. Okay, this is more of one of those ones that's about realization and again, reinforcing this idea that the words constant speed or constant velocity are trigger words for, hey, the net force is 0. Okay, so if I'm pushing something with 90 newtons of force and it's moving at a constant speed, that means there's something resisting me with exactly the same amount of force in the opposite direction. Okay, so that's all there is to that one, is just realizing that that's what that means. Okay, how many people have done 19? Okay, so is this very much like the lab we did yesterday? Number 19, right? We got something on a horizontal frictionless surface. It's attached to another mass, okay, over a pulley, just like we did in the lab yesterday. Okay, we know that the box is 1.0 kilograms and that the hanging mass is 1.5 kilograms. We know there's no friction on that surface. Okay, the big thing with this question is just reinforcing the rules of a system. Okay, and that is that we have to use how much mass?
All of it.
All of it. Okay, the net force acts on all of the mass in the system. This force of gravity here is the net force. It tells us the system is frictionless, so okay, our force of gravity that's pulling down on the 1.5 kilogram box, okay, has to be our net force. So 1.5 times 9.81 gives us our net force. And then we just have to remember that we are accelerating both boxes, so we simply divide that number by 2.5, the combined mass of the system, and that gives us our 5.9 meters per second squared. All right? Everybody with me there? Yeah? Okay. All right, keep going on those guys. Okay, in a couple more minutes, we'll do the next ones in line there. Okay, I kind of told you about this one before where there's this strange situation of somebody standing on a bathroom scale in an elevator. Okay, the big thing to remember about that is that the bathroom scale tells you the upward force. Okay, it's telling you how much force the floor is pulling on the person inside or pushing on the person inside in an upward direction. Okay, so the person is normally 725 newtons. So if we're drawing this as a free body diagram, that is the person's weight, 725 newtons. Okay, the elevator scale reads 775 newtons. So that means the floor of the elevator is pushing upwards on the person with more force than their actual weight. Okay, which means this person is moving up. The net force will be up. In fact, the net force will be exactly 50 newtons. 775 minus 725. And so our net force is 50 newtons up. Now that we know that, we can calculate the acceleration. But first, we need to know their what?
Their mass.
Their mass. Can we find that if we know their weight?
Yes.
Yes. Okay, because we assume that this is happening on Earth. Okay, so mass will be the force of gravity divided by the acceleration due to gravity. So 725 divided by 9.81, okay, is going to give us their mass. That's really the only trick to the question, is that you have to calculate the mass, and then it's just 50 divided by that number, okay, net force divided by mass, and you get that their acceleration is 0.677 meters per second squared up. Okay, how about 24? Are we good to go over 24? Okay. Okay, so what kind of question is this one?
Around.
Yeah, it's an inclined plane. Okay, and it's got that trick in it where I don't tell you the mass of the box, I tell you the weight of the box. So I'm giving you this force here, and it is 325 newtons. All right, I also tell you that the angle of the ramp is 30 degrees. Okay, so the other forces involved, the normal force from the ramp pushing up, that won't make any difference to this question. Those two forces, the net force of them is F parallel. That is the vertical component of gravity acting down the ramp. Okay, so if I'm going to find F parallel, which I need, okay, then I have to go sine of the angle, because it's the opposite side, times 325 newtons. Okay, so half of 325, okay, so cosine 30 times 325. All right, so we're going to have 162.5. Okay, so okay, it's frictionless, so that's the only force. Same trick as in the last question. I gave you the weight, you need the mass, divide the 325 by 9.81 to get the mass of the box, 33 kilograms, okay, and then divide our net force by the mass, 4.91 meters per second squared down the ramp. Okay? Everybody all right with that one? Okay, that's about as basic as a inclined plane question gets. We're going to make them more complex there, as you can see, as you start on to the inclined plane questions. All right, so I'll give you a few more minutes to get ahead of me again. Okay, working on those inclined plane questions. All right, so these blocks, they were enormous. It took crews of a lot of people to roll, and they actually rolled them on trees. Okay, so they had like just tree trunks like rolled, and they would roll the blocks up on these tree trunks. And then when one trunk would get to the back, they would move it to the front, okay? And they would keep moving it up the ramps. There were no aliens involved, okay? This was like massive manpower and long ramps, okay? In fact, there's evidence that said they kind of spiraled up the pyramid and just used the levels of the pyramid as they built it to continue to move up. Okay, so we have that these were angled at 10 degrees, okay, and that the mass of those stones were 5,000 kilograms, okay. So the other thing we know here is the acceleration is 0 meters per second squared, which also means that F net is 0. So the forces involved, friction was 800 newtons on each block. What else is acting down this ramp?
Force net,
Nope.
I mean, parallel?
Parallel, right. F parallel. F parallel is involved on every single ramp. F parallel also is here. And then there's the applied force. Those three forces add up to?
Each other's 0?
0. Right? These are being pushed at a constant velocity. So let's go to that internal triangle that's present on every single inclined plane. Right? We know that this side here is F parallel, and this side, or this angle, is the same as the angle of incline. So gravity I can calculate. It's going to be 49,050 newtons, 5,000 times 9.81. Okay, so I've got that side, and now I can calculate the F parallel because I have the angle and the hypotenuse. F parallel is always the sine of the angle, in this case 10 degrees, times the force of gravity, in this case 49,050 newtons. Okay, so if I go sine of 10 degrees times 49,050 newtons, all right, I've got that the F parallel is 8,517 newtons down the ramp. All right, so if it's not accelerating and the net force is 0, then the force up the ramp has to equal the forces down the ramp, right? Because they all add up to 0. Okay? If I know that F net is the vector sum of all forces, F parallel, plus the force of friction, plus the applied force up the ramp, okay, and F net is 0, well that means that F parallel plus the force of friction equals negative applied force. Okay? They're equal, but they're in opposite directions. So all I have to do is add these two numbers together, which is why I get 9,317 newtons up the ramp. Well, it's actually to 3 significant digits. We have to put it in scientific notation. Okay, everybody with me there? Okay. Questions like this, like they start to sound like there's a lot to them, but all inclined planes really break down to the same things. Okay, it's just I can change the context to make it more and more misleading or meandering or whatever, just to try and throw you off. But in the end, it comes down to that triangle is the same inside of every inclined plane. Right? How many people are done number 5? Okay, I'll give you some more time on that. All right, so number 5 is just kind of backwards. You have to work back to get the incline, but it still sets up just like any other inclined plane. It's just that now theta is unknown. We still have a box sitting on a ramp. We know the box is 65 kilograms. In this case, the box is a child on a soapbox derby racer. Okay, so we got our force of gravity here. We're going to know that number because it's just 65 times 9.81. Okay, so 637.65 newtons. Okay, that side's F normal, but I'm not going to need that. And then this side here is F parallel. All right, and I don't know what theta is. All right, so the other things we know. Friction is opposing with a force of 25 newtons. That means it's acting up the hill. And then this force is F parallel. They also tell me the acceleration, 4.25 meters per second squared, which means I can calculate the net force right off the bat because I know the mass and I know the acceleration. So 65 times 4.25. All right, so 276.25. That's my net force. Since only two forces directly contribute to that, I can also do a vector sum of all forces calculation. F net is F parallel plus the force of friction. Now I can calculate F parallel. So F parallel will be 276.25 minus negative 25, because friction is acting in the opposite direction of the net force. Okay, that's usually the part people miss on this question. Okay, so that is going to mean then that I've got that 276, and I'm just going to add 25 to that. Okay, there is my F parallel, 301.25 newtons. Okay, it makes sense. It's got to be 25 newtons bigger than the net force. Okay, we know the object or the kid is rolling down the hill. Okay, that means F parallel has to be bigger than the net force, or sorry, than the force of friction and the net force. Okay, now that I've got that, now I know this side of the triangle. So now I can work backwards and I can get theta. I have the opposite side and the hypotenuse. So the sine of theta equals 301.25 over 637.65. Okay, so if I want to get theta, it's just inverse sine of that calculation. Uh, 637. Okay, so that ramp or hill is angled at 28.2 degrees. Okay, it's not too often that I do a question where I'm asking for the incline, but this one just made you have a slightly different thought process using the same givens, which is of course what we're looking for. Okay, I'll give you a few more minutes to get ahead of me here on some of those more challenging ones, okay, and we'll go through them. Okay, so on number 9, we got avalanche, okay, moving down the mountainside, and the slope is 50 degrees. So, you know, obviously a much steeper situation. 50-degree slope, okay. The mass of the snow is 2,500 kilograms. This is why you don't want to get caught in one of these, okay. It's usually like a rolling, crushing, kind of blunt force trauma kind of situation that you don't want to be in, okay. We'll have F parallel here. And we'll have that we are looking for this force of friction that is somewhat slowing the acceleration of the avalanche snow on its way down. Okay? So here's what we know. We know the acceleration is 6.5 meters per second squared. Is that fast? It's really fast. Like, you're not outrunning this fast. Okay? If you were on a set of skis and you did nothing but point them straight down the hill, you probably still wouldn't outrun it. Okay? Not that you could ever just point your ski straight down the hill, because you get going, well, as fast as an avalanche, and most people can't handle that. Okay? So I can calculate the net force right now, okay? Because I know the acceleration and the mass. So we'll do that step. We'll take our 2,500. Okay, and we'll multiply it by the 6.5 meters per second squared. There's our net force, 16,250 newtons. All right, that's the net force. Now, I can also calculate what F parallel is because I can calculate the weight of the snow, okay, and I know the angle. So let's calculate the weight of the snow. Okay, it's going to be 2,500 times the 9.81. All right, so there's the weight of the snow. And then we can calculate F parallel in the same way we always do. Go sine of 50 degrees, okay? And then times that number times the hypotenuse. Okay, so there's our F parallel, 18,787. Okay, well, since I know what the net force is, and I know only F parallel and friction are acting, whoops, I put F parallel up and down, sorry. Force of friction and F parallel are the only two that are leading to that, then I should be able to calculate what that force of friction is, because F net is the vector sum of all forces. So I just take the F parallel over here, and I'll have F net minus F parallel, and that'll get me the force of friction. Since F parallel is bigger, okay, than F net, I'll get a negative number. And that's good, because friction should oppose up the hill. So we subtract those two numbers, and what we're left with is friction is 2,540 newtons up the hill. Okay, resisting in that direction. Okay, any questions on that one? How many people got the pulley one done?
In about 2 minutes.
Okay, we'll talk about that one maybe tomorrow.
Drill, so everybody can be ready to go for that. Staff, just a reminder that your status cards are left at your door on the way out. And then your quick attendance sheets can be brought to the supervisor either in the front or the back. And one more reminder for students, we do have a representative from U of C coming today, so once the fire drill is released, they will be set up in the atrium. So if everybody can get ready, so 2 minutes, we will have our drill.
Okay, you guys remember where we go? Okay, we go out the doors by the vending machine and then out to the football field. Okay, that is our path. You can take what you got. You can't shoot it. Yes, I established that down was positive. If you want to make a positive, then the other number would be negative. And you're subtracting the negative number and you get positive. It's totally up to you which one you get. Take them with just meet me for attendance. Please don't fail.